reaction is going to happen? Because I gave you the product. Okay. What happens if we did something like this?
It's debatable.
Now maybe you could debate it, except what have we talked about? We know it happens. Okay? With the context knowing it happens, that opens up a lot of things. And that makes this very wishy-washy, because virtually everything we've done has been saying, well, no, here's the reason why it happens. There is still a reason why these things happen here. Okay? Nitrogen and oxygen are so close in reactivity that these are heavily based in equilibrium. So if I want to form the imine, what should I do? What can I do to help the imine form? This whole chapter started with a fun little slide about equilibrium. And because we're looking at equilibrium, we have to be thankful for our nice French guy.
Increase one reactant?
I could increase the concentration of ammonia. If I push the concentration of ammonia through the roof, now what happens? Okay? None of those steps that you got drawn on the boards may be particularly favorable, but I've now put so much ammonia in there that it's forcing the equilibrium that direction. What else could I do? I could try to remove the amine. That's going to be really hard to do. Why is it going to be hard to remove the amine? How would you typically remove a product? Distillation, which relies on boiling points. And boiling points are dependent on intermolecular forces. What are the intermolecular force differences between the amine and the carbonyl? They're pretty similar. If anything, the carbonyl is lacking hydrogen bonding and the imine has it, which means if we try to distill, what happens? The carbonyl goes out and we lose our reactant. That becomes problematic. Okay? Without a reactant, we can't make products. Okay? Is there something else that we could do? Yes. As a hint, the reaction is not balanced. Where did that oxygen go? Okay. Not only where did that oxygen go, but where did two of the hydrogens go on the nitrogen? Okay. Those two hydrogens were transferred from the nitrogen to the oxygen to form water. We have water as a leaving group. How could I possibly remove water from the reaction? Yes, distillation. Distillation's not going to work because water has hydrogen bonding, and it's probably going to have a lower boiling point or higher boiling point. I could go through and add molecular sieves or some other compound in there that scavenges water and removes it from the reaction. Okay. Sodium sulfate is the kind of crude version of that. Sodium sulfate is a salt that just soaks up water. The fancier version is known as molecular sieves. Really all they are is a super dry piece of clay that sucks up water. That's about it.
So you're saying principle, again, remove the water,
Yep.
rise
Yep.
to get more of all products,
Exactly right. Yep.
but only one. Right?
It's going to form both products if I
No,
remove
what
water.
I'm saying is only remove one
Well, we can't remove the amine.
because it's difficult.
Yeah, there isn't a way to remove that one. So the only one we can remove is water. Okay, which is going to bring up potentially another question further on down the road. This was an equilibrium reaction, right? So what could I also do? What if I had the amine? I could turn the amine into a carbonyl by doing what? Adding a ton of water. That's going to now help push the reaction the other direction. Okay? A catalyst will be helpful, as some of you started to address with your mechanisms. An acid catalyst tends to be the most common one with these. Okay? But it does not have to be an acid catalyst. It can go under basic conditions. Okay? Okay. You've already got your reactions up there, so let's take a look at some reactions. You got a whole bunch of reactions. Take a swing at what you think the products are. You've got the basic pattern that we just looked at for how we're converting. Draw out what you think the product is. So let's go ahead and take a look at these. So this is our first quick just kind of cheat. Take the hydrogen, takes the oxygen, make water, put the nitrogen where the oxygen is. Done. Okay. Mechanistically, what's happening, and this is going to look awful, but I don't want to draw all these structures. The nitrogen attacks. We break the pi bond. Okay. The oxygen removes a hydrogen. Nitrogen attacks a second time, kicks out hydroxide. Oops, I should have color-coded that. Kicks out our hydroxide. That hydroxide attacks a second hydrogen and puts it on the nitrogen. Okay. So you could boil that down to roughly 3 mechanistic steps. And you know what you guys should be really proud about is that you're all cringing at what was just drawn up there. And the only people that would cringe about that would be organic chemists. So good job. That's pretty fantastic. Next one. Most people would look at, oh, that's beautiful. It's a rainbow. The next one. Okay. We have 2 sources of electrons to attack our electrophilic aldehyde. We have the nitrogen or the oxygen. Which one should attack? Okay. A suggestion was made for the nitrogen. Why would the nitrogen be the one to attack? Why is the nitrogen the nucleophile? Oxygen actually has a greater desire for electrons. So if we look at this desire for electrons, that's electronegativity. Oxygen is more electronegative. Fair point. Red nitrogen versus blue oxygen.
Is it because nitrogen can keep reacting? Is that what it says?
Why is nitrogen a better nucleophile than oxygen? What is the definition of a nucleophile?
Oh, is it?
It shares electrons. What is the difference between nitrogen and oxygen? Oxygen's more electronegative. By being more electronegative, what is it doing to the electrons? Holding them. The complete opposite definition of a nucleophile. The nucleophile must donate those electrons, which means our nitrogen is our nucleophile. We still have those 2 hydrogens on there, so we can go ahead and draw out our product. I used to know the name of that functional group, but I don't. Oxime? Yeah. There you go. Oxime or oxime, I don't really know. It's one of those. But it is a perfectly valid structure and useful reagent. Okay. Next one. Bless you. Anybody potentially nervous about the product of the next one? Yeah, why? There's only 1 hydrogen. In all the other cases, we removed 2 hydrogens. Okay? And the examples that we looked at on the boards with those initial slides, we had 3 hydrogens where 1 was left. In the other 2 examples, 2 hydrogens disappear. In this case, we only have 1 hydrogen. Okay? So one of the kind of gut reflexes that students go through and do, particularly because I gave you this pattern, was to draw this structure, which my computer locked up and decided not to draw for you. So let's try that again. Okay. That structure is sorta okay. What is wrong with it? I have a positively charged nitrogen. Okay. If we think back to that ugly mechanism at the very beginning, the nitrogen attacks, it breaks, the oxygen removes the hydrogen, it breaks, the nitrogen attacks again and kicks out that structure. Do we have another hydrogen to remove? No, which means nitrogen donated all of its electrons, making it positively charged. Is a positively charged structure stable? No. Nitrogen wants its electrons, so what does it do? It sucks those electrons back. And we'd have a positive carbon. What's the relationship between the purple and the red carbon, or red structures? Resonance. Okay. All we've done is moved electrons. Let's get that lone pair on the nitrogen again. But that's again still a charged structure that's no different, but that structure gives us some information. Does the carbon want to be positive?
No.
What is it missing? Electrons, right? And the thing that we kicked out was what? OH minus, right? Where are there electrons in that structure? Do not say nitrogen.
Wait, in the OH?
In the red structure.
Oh. Where are the-
Because we could try and have the oxygen attack. That's going to be a steric hindrance issue. That goes back to our acetals under basic conditions.
In the red structure, there's electrons? or
There are,
protons?
in all of the bonds. What'd you say? Well, that's an eraser. Hydroxide is a base. You can do an elimination reaction. Form the pi bond inside that structure. And now we have our final answer. All right, now you got that structure drawn. Can I draw some stuff over the top of it?
Like a sand thing?
What did I just draw over the top?
And an oxygen.
That's an enol. Plot twist, yay. Oh, you monkey. Dart knocking. Is this an enol? This can't be an enol, but this mimics the structure of an enol. Right? Okay. It can't be an enol because what does the OL mean? Alcohol. What is this? Well, it's an ene. Amine. So the enol chemistry that haunts us and will continue to haunt us shows up with nitrogens as well. And we end up with a slightly different version. We end up with enamines. The enamine is actually more stable than the enol. Why would that be the case? Ox is a good place to start on that.
Because oxygen is more electronegative.
Oxygen is more electronegative than the nitrogen, so what would it do to the electrons? It would pull them up so that it can hold on to all of them. Because the nitrogen is not quite as electronegative, it allows for the pi bond to form down there. Cool. Okay? For those of you in lab, you should get used to drawing enamines because the WMK deals with enamines in virtually 3/4 of that mechanism, which we need to announce, by the way. So don't let me forget about that. Bottom one. What's the reagent? The transition. How did I do that first step? Okay, I had an NH2 bonded to an NH2, where I removed 2 hydrogens and the oxygen. Okay, that sets me up with this fancy looking intermediate. Remember that whole oxime structure? This intermediate is similar to that, except we have 2 nitrogens there. The next fun part is that if we also follow this with sodium hydroxide, well, what is sodium hydroxide? A strong base. That strong base will go through and start removing hydrogens from this structure to produce officially water with the hydroxide. It will produce these 2 structures, nitrogen gas and a cyclohexane. More importantly, what did we do? We added 2 hydrogens directly to the carbon. Functional group change, what happened? We started with a carbonyl and we now have an alkane. We completely removed the carbonyl functional group. Okay. What allows you to do that? It's really that nitrogen-nitrogen structure there with some careful electron pushing acid-base reactions with our hydroxide will allow us to form nitrogen gas. Okay? And that, I believe, is actually the next slide. It's the Wolff-Kishner reduction. Okay, you're doing a full removal or a full loss of that oxygen. This kind of alludes to chapter 19 because this is one of the reagents that you would use in chapter 19. Okay, whoa, sorry, I thought the mechanism was there. To just set you up with that mechanism initially, okay, and yes, I'm going to be irritating on this. Okay, and really I'm only being irritating so that I can get to the important thing that I want to draw, which is this guy. Okay, what does the hydroxide come in and do? Grab a hydrogen. If it grabs that hydrogen, these electrons can then go over to that nitrogen. But that nitrogen would now exceed the octet. So I would have to break a bond. The bond I would have to break would be a pi bond. That pi bond then goes to our carbon, generating which structure? There's a benzene in there. What charge would that carbon become? Negative. Negative. I now have a negative carbon. Does carbon want to be negative? What can it do? Donate electrons to. What else is in solution? H2O. There's the first hydrogen in my reaction. Okay. That reaction continues to cycle, pulling off hydrogens. Eventually what ends up happening is we break the sigma connection between the nitrogen and the carbon, leaving us with nitrogen gas. And we might say, well, why would we drive this reaction? Well, how stable is nitrogen gas? Very stable. Not only is it stable as a gas, what does it do when it forms? It leaves the reaction. If we don't have that reagent, can we reverse the reaction anymore? No. Okay, so the reaction becomes an irreversible reaction because of that nitrogen gas leaving the reaction. Okay, so pretty neat. Okay. The next part of this then doubles back to our enolates. Okay, so this is going to be the second half, I don't even know if it's a half, second part of chapter 18. All of these are now going through and looking at the carbonyl and saying, how do we form an enolate? Okay, that enolate is now a nucleophile. That nucleophile can react with electrophiles. What are carbonyls? Electrophiles. So what we end up doing is taking the enolate, which we learned a whole bunch about in chapter 10, and we now have it nucleophilically add to carbonyls. Okay? Depending on which things we're doing it to or what products we get, we come up with different names. It starts off with the Aldol reaction, but then you'll hear reference to an intramolecular aldol known as, no, I got it wrong. I was going to call it the decapit. So just intramolecular aldol. We'll have crossed aldols, meaning instead of starting with the same aldehyde or same ketone, I have 2 different ones. Okay? All of those add layers of complexity behind the reaction that we just have to think about. When we move into the next unit, we'll talk about esters. Well, at that methyl group, is there a hydrogen? Is that hydrogen acidic? Why? Because it is alpha to a carbonyl, which means that carbon can become a nucleophile. And that nucleophile could potentially nucleophilically add to more carbonyl compounds. So we end up with Claisen reactions. They're nothing more than an aldol reaction, but starting with an ester instead of an aldehyde or ketone. Okay, so virtually all of those reactions are the same style or the same core principle. So we'll look at the bulk principle right now, and then that's pretty much where we'll end chapter 18. We will come back to those reactions after exam 2, okay, and look at those in much more detail at the complications behind those mechanisms. But we don't have enough time to address those, which means Monday we'll look solely at chapter 19, which is our reduction and oxidation. So what we're pretty much removing from the exam is most of the aldol type stuff. Okay? What's that? Oh, sorry. Then I can put it on the exam. We start with a base. Okay? Because it's a base, or actually we could look at this. What could that species act as? This guy right here. Nucleophile, way to take the ungiven answer, that's good. Or base, I literally just said it could act as a base, right? So it could act as a nucleophile or as a base. If it acts as a nucleophile, it would attack, right? To form what? Not an ether. No. What is it forming? That would be unstable, so we put a hydrogen on it. A hemiacetal. Are hemiacetals stable? No. So yes, the oxygen can act as a nucleophile. It doesn't take me anywhere productive. So instead it could act as a base. Is there an acidic hydrogen? Yes. The alpha position to our carbonyl. Why is that hydrogen acidic? Because of resonance to stabilize it. Resonance through which structure? The enolate. Okay? Which of those two compounds is the more reactive one, the one I should be using in this next step? Why the bottom one? What's the difference in energy between those two structures? Oxygen can hold a negative charge, which makes that resonance structure the best one, which then means don't use the best one to look at a mechanism. You need to look at the worst one.
The worst best, you always say.
The worst best. That's still not the best. Okay? That structure is our best Lewis structure because it puts a negative charge on the atom that can hold it. That is useful. That explains why I can remove that hydrogen. But it does not explain the next step of the reaction. The next step of the reaction is now looking at the carbon as a nucleophile. Where is there an electrophile? The carbonyl. But didn't I do that already? That's not really an electrophile. The same one. I bring in another molecule of it. And I can now go through an attack. Okay? One of the options that you could think about in here is if you were put in this room and could just start punching things, right? What are you going to punch?
Other people.
Other people. If all of the people were removed from the room, what are you going to end up punching?
Computer.
Yourself. Okay? You can react with yourself. Okay? Same thing is happening here. When we run that reaction, it's not a single molecule, it's billions of molecules. You have to remember that. There is not only one. There is not.
Then why can it react with that?
It can continue to react with it 1,000,000 times until the chemistry is done. Okay? And it is proven that that can happen. If we go through this reaction, what happens? It attacks. Okay? If we evaluate kind of color coding behind this, here's our active nucleophile species. There's our active nucleophile carbons. That went through and reacted with another aldehyde. That's your other aldehyde. Okay? Is the oxygen stable? Good, no, because it's charged. So what does it do? It picks up a hydrogen, and we form this structure. What functional group has an OH? Alcohols. What functional group has that? So we have an ald for aldehyde and OL, or sorry, AL, I always forget the D there. ALDOL. That's our aldol reaction. Okay, that's the name. That can continue to react because we have hydroxide. What is special about hydroxide? It's a crap leaving group. But what can you tell me about the alpha position to the carbonyl? It is acidic, and it is in fact more acidic than our starting structure. So what happens? Our base reacts, removes a hydrogen, and we eliminate. Okay? Back to Preeti's question, couldn't this continue to react? It did. But now what happened to the alpha position? That alpha position is no longer acidic because the pi bond changes the electronegativity and prevents it from reacting. That structure now cancels the reaction and it can't continue forward. Why is this product better than the starting aldol or the final, an intermediate aldol? Cass was suggesting this. Those pi bonds are conjugated through resonance. That makes this structure lower in energy, and it makes that last step irreversible. Okay? With that, we'll go ahead and stop.